Hello, my name is Victoria Nizzi. I'm an undergraduate student here at Michigan Technological University in Mechanical Engineering and Material Science Engineering. I have been working with the Material Science Department SURF team on biodegradable alloys to be used in medical devices. For the year of 2020-2021, I was awarded the Michigan Space Grant Consortium undergraduate fellowship to be used for computer modeling to simulate and predict the biodegradation of a magnesium alloy fractured plate. Currently, titanium alloys and stainless steel alloys are being used in the industry for fixation plates, and they work very well, except they can fracture while they're inside the patient, which would necessitate a secondary surgery and increase the amount of risk that the patient is undergoing. To help solve this, we've been working to create biodegradable alloys that would absorb back into the system after the fracture has been healed. This computer program would help with experimentation so that we do not have to undergo as much in vivo and in vitro experiments to save time and money. The simulation is for a 70-kilogram male with a transverse femur fracture with 6 3.5 millimeter diameter cortical screws in the plate. The cortical bone and magnesium zinc ECAP alloy properties are as labeled with the following friction coefficients. The loading cycle is based off of one step that the person may take, and it needs to last for at least 4 times 10 to the 6 cycles, which is about the time it would take for the fracture to fully heal. So the fracture plate itself cannot fail before we hit 4 times 10 to the 6 cycles. The results of this, as shown, were in mechanical property contour plots of the simulation, and it showed that it had a deformation, equivalent stress, equivalent strain, and fatigue life as follows. You can see the fatigue life is 1 times 10 to the 7 cycles, which is over twice what is necessary for the bone to heal, which is good because that means that it will not fracture inside the body. And the equivalent stress is approximately 110 megapascals and is shown mostly in the top blocking portion of the fixation plate closest to the femoral head. This simulation was successful as it showed similar results as the B. Schwartz finite element model of locking plate of a fracture, resource number 2 that I'm referencing, and it can be used by my team in further alloys we will be creating and testing so that we can avoid the cost and time of in vivo and in vitro plants. Thank you very much.